Hello, I'm David Silver from Udacity, and this is lesson number 8 of the Udacity Self-Driving Car Engineer Nanodegree program. It's called Convolutional Neural Networks. So this is the 8th lesson of the Self-Driving Car Nanodegree program, Convolutional Neural Networks. Vincent explains the theory behind convolutional neural networks and how they help us dramatically improve performance in image classification. And Vincent, of course, is Vincent Van Hoek, principal scientist at Google's Deep Brain platform. We're really lucky to be able to learn from someone like him. That's Vincent, in fact, right there. So Vincent gives a kind of overview of how convolutional neural networks function. Convolutional neural networks are a type of deep neural network that is particularly well suited to working with images, so what we would photographs like we would capture from a camera. And in fact, how convolutional neural networks function is that you might take an image like this, so say an image of a dog, and the goal is to train the network to recognize this as an image of a dog, so that when we send this image into the network tells us, oh, this is a dog. Or if we send a cat to the network, a photograph of a cat, the network would say, oh, this is a photograph of a cat. So how does the network learn to classify cats and dogs and other things? Well, the network might start by finding small parts of the image and identifying them as smaller elements. So this might be a curve here that the network recognizes as a curve, or this might be a nostril, or maybe just a hole. And it might even be more basic than that. The network might just start by recognizing colors like black or red or blonde, and then it would build up those smaller elements into more sophisticated features like an eye or a nose or fur. And then eventually those basic elements would feed up to more sophisticated features, which would ultimately help the network categorize that collection of features as a dog. And somewhat more technically, what happens is that the neural network has this thing, or a convolutional neural network has this thing called a filter. And the filter passes over each layer of the network. So if you imagine the first layer is just the input image, the filter slides over the input image, and each pixel within the filter, within this red box, is connected to an artificial neuron in the next layer. And by combining all of the pixels within the filter, within this red box, the next layer of the network might recognize what's in this filter as perhaps fur or the color blonde or something else. One of the vexing parts of deep learning is that the neural network, in fact, may recognize what's in the filter or may identify a feature from what's in the filter as something that we as humans can't even really describe. But the network just learns it because it figures out that's the best way to ultimately categorize the whole image as a dog. Because that's the goal, is to use these filters sequentially from layer to layer to layer to ultimately classify the image as a dog or a cat or whatever it's supposed to be. And you can see kind of another illustration of this. This filter is connecting all of these artificial neurons here to an artificial neuron in the next layer. Or if this were the input layer, these might be all of these pixels to an artificial neuron in the next layer. So that's kind of conceptually how deep learning works. And as students go through the lesson, there are lots of quizzes where students both have to think about how filters work and convolutional layers work conceptually. Convolutional neural networks in particular can take up a lot of memory and computational power because of all of the weights that are necessary to connect each of the filters, or all of the weights that are necessary within the filters to connect artificial neurons from one layer to the next layer. Those weights can really add up to pretty substantial. So you need to keep track of how many weights or parameters the network is storing. And as we go on, students learn to program convolutional neural networks, there are exercises. As Sebastian likes to say, you don't lose weight by watching other people exercise. In order to learn to work with convolutional neural networks, you really have to write the code yourself, and that's a big part of this lesson. As we get towards the back half of the lesson, we move on from pure convolutions to some advanced deep learning concepts that typically go along with convolution. So things like pooling layers that help reduce the number of parameters and weights that you need to keep in the network, and things like one-by-one convolutions, which can transform how you look at images. And ultimately, the lesson ends with a lab, which is implementing Linnet in TensorFlow. Linnet is one of the most famous deep neural networks, and it's actually a convolutional neural network. It was invented by Jan LeCun in the late 1990s and used for many years to classify characters, things like letters on a postal envelope or letter or digits on a bank check. And coding up Linnet and using it to identify characters is kind of a classic foundation of how to learn to work with convolutional neural networks. So as part of this lesson, we provide students with a Jupyter notebook that students can then walk through and then use to build up Linnet and train it to identify characters. And we provide a solution here in case you have a little bit of trouble figuring out how Linnet works. This gives you a sense of what you need to do in order to get a convolutional neural network built and trained. Here is one of the concepts in the lesson. In this particular concept, Vincent van Hoek walks through how the architecture of a convolutional neural network is set up. Enjoy!
Let's talk about convolutional networks, or ConvNets. ConvNets are neural networks that share their parameters across space. Imagine you have an image. It can be represented as a flat pancake. It has a width, a height, and because you typically have red, green, and blue channels, it also has a depth. In this instance, depth is 3. That's your input. Now imagine taking a small patch of this image and running a tiny neural network on it with, say, k outputs. Let's represent those outputs vertically in a tiny column like this. Now let's slide that little neural network across the image without changing the weights. Just slide across and vertically like we're painting it with a brush. On the output, we've drawn another image. It's got a different width, a different height, and more importantly, it's got a different depth. Instead of just R, G, and B, now you have an output that's got many color channels, k of them. This operation is called a convolution. If your patch size were the size of the whole image, it would be no different than a regular layer of a neural network. But because we have this small patch instead, we have many fewer weights, and they are shared across space. A ConvNet is going to basically be a deep network where instead of having stacks of matrix multiply layers, we're going to have stacks of convolutions. The general idea is that they will form a pyramid. At the bottom, you have this big image but very shallow, just R, G, and B. You're going to apply convolutions that are going to progressively squeeze the spatial dimensions while increasing the depth, which corresponds roughly to the semantic complexity of your representation. At the top, you can put your classifier. You have a representation where all the spatial information has been squeezed out and only parameters that map to content of the image remain. So that's the general idea. If you're going to implement this, there are lots of little details to get right and a fair bit of lingo to get used to. You've met the concept of patch and depth. Patches are sometimes called kernels. Each pancake in your stack is called a feature map. Here you're mapping 3 feature maps to k feature maps. Another term that you need to know is stride. It's the number of pixels that you're shifting each time you move your filter. A stride of 1 makes the output roughly the same size as the input. A stride of 2 means it's about half the size. I say roughly because it depends a bit about what you do at the edge of your image. Either you don't go past the edge, and it's often called valid padding as a shortcut. Or you go off the edge and pad with zeros, in such a way that the output map size is exactly the same size as the input map. That is often called same padding as a shortcut.
I hope you enjoyed this lesson about convolutional neural networks. If you are excited to learn more about deep learning and self-driving cars more broadly, I encourage you to sign up for our self-driving car engineer nanodegree program. You can find it at udacity.com/drive, and I hope to see you in class. Bye-bye.